So now I want to finish up the work with Stokes' theorem by talking about how we interpret what we're getting out of Stokes' theorem, and in particular about interpreting the curl. With Stokes' theorem, we now have the ability to calculate an average circulation of our vector field F on a surface S without actually having to find the area of the surface first. And that's pretty cool. Here's how it works. My average circulation is given by 1 over the area of my surface times the closed integral over C of f dot dr, which is equal to 1 over the area of my surface times the double integral over S of del cross f dotted with n ds. But keep in mind that dot products are always scalars. That means they're constants. So that del cross f dotted with n is a constant, and constants can be brought out of the integral, so that this can be rewritten as 1 over the area of S times del cross f dotted with n times the double integral over S ds. But the double integral over S ds is just the area of my surface, so that my area that I get from this double integral will cancel 1 over the area that I put into my work to find the average circulation. And what that tells me is that just del cross f dotted with n will give me my average circulation. So I don't have to do an integral, I don't have to find a surface. I simply take del cross f, dot it with n, and it will give me my average circulation. Now, if I take a general rotation field given by F is equal to A cross R, where A is a vector with components A sub 1, A sub 2, A sub 3, and it's a constant non-zero vector, and R is a vector with components X, Y, Z, we know that F represents the rotation about an axis in the direction of A that has an angular speed of omega that's given by the magnitude of A. So when I take this general vector field and compute del cross F with it, I get del crossing the cross product of A cross R, and when I do that computation, I get 2 times the vector A. Now, if we take S to be a really small circular disk centered at some point P, whose normal vector n makes an angle of theta with the axis of rotation given by A, our average circulation becomes del cross f dotted with n, which is equal to 2 times the dot product of A and n. But using what I know about dot products, this just gives me 2 times the magnitude of A times cosine of theta. So this gives me my average circulation for a general rotation field. Now let's interpret what we're talking about with this average circulation. I know that del cross f dotted with n is equal to 2 times the magnitude of A times cosine theta. I can also read that as the scalar component of del cross f at point P in the direction of n. That's what that mathematical statement means in English. This means that 2 times the magnitude of A times the cosine of theta is the average circulation of F on S. The direction of del cross F at P is the direction that maximizes the average circulation of F on S. This is the direction you're going to want to turn a paddle wheel, for example, if it's located at point P, in order to obtain a maximum angular speed of circulation. This argument for average circulation can be extended to apply to a general vector field with a variable curl as well. Let's work an example. I want to compute the curl, sketch the curl, and interpret the curl for the velocity field that is given by v is equal to a vector with components 1 minus z squared, 0, and 0. The curl is del cross my vector field. So I'm going to take del cross v, which is equal to the determinant of a 3 by 3 matrix, and I get 0 in the I hat direction, minus 2z in the j hat direction, plus 0 in the k hat direction, which gives me a vector with components 0, negative 2z, and 0. If I plot this curl field, I notice that I get arrows that progressively get larger as I move away from the center, and that they change direction above the XY plane versus below the XY plane. The curl indicates that there's a maximum rotation in the direction of the y-axis because that's the direction my arrows are pointing in. With respect to the positive z-axis, the rotation is counterclockwise when z is less than 0, and it is clockwise when z is greater than 0. The amount of rotation in either direction, clockwise or counterclockwise, increases as I move away from my z-axis. So that's my interpretation of my curl. I want to make a few more comments about Stokes' theorem before we finish it up. If I have two surfaces that each correspond to the same boundary curve C, and both surfaces have a consistent orientation with C, meaning a normal vector for my surface 1 will be consistent with a normal vector of my surface 2 in terms of the direction that they point, then the integrals of del cross F dotted with NDS on the two surfaces, in this case, will be equal. Now these two surfaces might look like the cap of a sphere inside a paraboloid where both surfaces are bounded in the xy plane by a circle with radius r. I could sketch something that looks like this, where I have a blue paraboloid curve centered on the z-axis, and I have the cap of a sphere that is centered around the z-axis, and they both intersect at a curve C in the xy plane. The normal to my surface 1 points outward. The normal to my surface 2 also points outward. These two normal vectors are consistent with the direction or the orientation of C, where C is positive in the counterclockwise direction. This means that the double integral over S of del cross F dotted with n sub 1 ds sub 1 will be exactly equal to the double integral over S of del cross F dotted with n sub 2 ds sub 2. On the other hand, if I have two surfaces that correspond to the same boundary curve C and form a closed surface, but now n sub 1 points out of the enclosed region from S sub 1, while n sub 2 points into the enclosed region from S sub 2, or vice versa, n sub 1 could point in and n sub 2 could point out, then in either case, the integrals of del cross F dotted with NDS on the two surfaces will be equal in magnitude but opposite in sign. The sketch that I've provided is a sketch of an upward opening paraboloid and a downward opening paraboloid that intersect on a boundary C in the xy plane. My n sub 1 vector points outward from the surface S sub 1, while my n sub 2 vector points inward on my S sub 2 surface. In this case, the double integral over S of del cross F dotted with n sub 1 ds sub 1 plus the double integral over S of del cross F dotted with n sub 2 ds sub 2 will identically equal 0 because the two integrals are equal in magnitude, opposite in sign. What this tells me is that if del cross F is equal to 0 throughout an open simply connected region D of R3, then the closed integral over C of F dot dr is equal to 0 on all closed simple smooth curves in C and D, and F is a conservative vector field on D. In other words, if the curl is 0, it implies I have a conservative field. So let's work an example. I want to use Stokes' theorem to find the circulation of the vector field F is equal to a vector with components 3x squared y, x cubed plus 2y, and 2y squared z around any simple closed smooth curve C. Del cross F is equal to a vector with the del operator components crossed with a vector with components 3x squared y, x cubed plus 2y, and 2y squared z. I set up the determinant of my 3 by 3 matrix, and I end up with 0 in the I hat direction plus 0 in the j hat direction plus 0 in the k hat direction, or a vector with components 0, 0, 0. Since del cross F is 0, we have a conservative vector field. I want to work another example where I'm going to do a little bit more with applying Stokes' theorem. In a special case of Ampere's law, we get the closed integral over C of B dot dr is equal to mu I, where C is any closed curve through which a current carrying wire passes. Mu is a physical constant, and B is the magnetic field, and I is the current in the wire. If we let the current I be given in terms of a current density vector J, such that I is equal to the double integral over S of J dotted with N ds, where S is an oriented curve with C as a boundary, we can use Stokes' theorem to give an alternative form of Ampere's law. So I'm going to start with mu I equal to the closed integral over C of B dot dr. This is equal to the double integral over S of del cross B dotted with N ds. But I know that I is the double integral over S of J dotted with N ds, so that mu I becomes mu times the double integral over S of J dotted with N ds. And since the two double integrals are equal to each other, I can write the double integral over S of del cross B dotted with N ds minus mu times the double integral over S of J dotted with N ds is equal to 0. Now notice that both of these double integrals have the same variable of integration and the same limits. This means that I can pull them into a single integral. The single double integral becomes the double integral over S of del cross B minus mu times J dotted with N ds. And because this has to equal 0 for all closed surfaces S bounded by C, and considering that we're free to choose S and C, the integral itself has to equal 0, which means that del cross B has to equal mu times J. So that del cross B is equal to mu times J is an alternative form of Ampere's law. So now you get to try it. Pause the video and use Stokes' theorem and a surface integral to find the circulation on C of the vector field given by F is equal to a vector with components negative y, x, and 0 as a function of phi, where S is a disk enclosed by the curve C, such that R of t is equal to a vector with components cosine phi, cosine t, sine phi, cosine t, where 0 is less than or equal to t, which is less than or equal to 2 pi, and 0 is less than or equal to phi, which is less than or equal to pi halves, is a fixed angle. Determine at which value of phi the circulation is a maximum. When you're ready, restart the video to check your understanding. But I'm going to give you a hint. Don't forget, phi is fixed. It can be treated entirely like a constant here. So I'm going to use Stokes' theorem, which states that the closed integral over C of F dotted with dr is equal to the double integral over S of del cross F dotted with N ds. I have to compute del cross F first. I set up the determinant of a 3 by 3 matrix, and I get 0 in the I hat direction, plus 0 in the j hat direction, plus 1 in the k hat direction, which is equal to a vector with components 0, 0, 2. My normal vector is given by t sub r cross t sub t. I set up my determinant for my 3 by 3 matrix with the first row populated with I hat, j hat, k hat. The second row is populated with the components for t sub r, which are negative cosine phi cosine t, sine t, and sine phi cosine t. And t sub t is the third row. Those components are negative cosine phi sine t, cosine t, and negative sine phi sine t. When I compute that determinant, I get a vector with components negative sine phi, 0, and cosine phi. Now what I want to do is put my vectors directly into Stokes' theorem. The double integral over S of the vector with components 0, 0, 2 dotted with a vector with components negative sine phi, 0, cosine phi ds gives me the iterated integral from 0 to 1 of the integral from 0 to 2 pi of 2 cosine phi r dt dr. I compute the innermost integral, and I get an integral from 0 to 1 of 4 pi cosine phi r dr. And when I integrate that, I end up with 2 pi cosine phi. The maximum circulation is going to happen when phi is 0 on the region between 0 and pi halves. At pi halves, cosine phi would be 0, and at 0, cosine phi would be 1, so that my maximum circulation is 2 pi at phi is equal to 0. This finishes up our work with Stokes' theorem. It's a powerful theorem, and in many cases it can save us quite a bit of work. Be sure and let me know if you have any questions.